In this video, we're going to talk about matrix operations. Our objectives are to learn how to define matrices in MATLAB, learn how to access and manipulate specific elements in a matrix, introduce some common built-in functions that are designed to work with matrices, and expand our understanding of earlier concepts to include working with matrices. You'll notice all of these objectives are very similar to what we did with vectors. And basically what we're doing is we're going to expand our understanding of MATLAB variables from what we've learned first with scalars, then with vectors, now to work with matrices. So what is a matrix? A matrix consists of a rectangular array or table of elements represented by a single variable. So here's an example A. An individual entry of that matrix is called the element. Similar to what we did with vectors. So in this example, here's element A23, and when we talk about those subscripts, we always say the row, then the column in the subscripts. That's located in the second row of the matrix A, and the third column of the matrix A would be element A23. Some fundamental matrix terms. A horizontal set of elements is a row. A vertical set of elements is called a column. The first subscript of an element indicates the row, while the second indicates the column, just like we just said with element A, 2, 3. The size of a matrix is given as m rows by n columns, or simply m by n. A 1 by n matrix is a row vector, and an m by 1 matrix would be a column vector. So you can think of vectors that we've already talked about are a special case of matrices with only one row or one column. So a lot of the concepts we talked about with vectors are pretty much the same for matrices. So let's talk about creating matrices in MATLAB. Rows are separated by semicolons. Columns are separated by spaces or commas. Again, similar or the same as vectors in vector definition. All the techniques that we use for creating vectors can be used to create individual rows or columns in a matrix. So here's an example where the first row of A is just created by entering numbers separated by spaces. The second row is created by the linspace command to create 5 evenly spaced elements between 2 and 20, and the third row is created with the colon operator using starting with 3, incrementing by 3, and ending at 15. And you see the result here. One note is when you're using commands like these, we need to have the same number of columns in each row. So that's very important. You can't have a matrix that's not rectangular. So sometimes you can run into an error when you're defining a matrix or doing matrix operations because you don't have the same number of columns in each row or the same number of rows in each column, however you want to think about it. So let's talk about element by element operations. Same as for vectors again here. But now the matrices must be the same size, which means same number of rows and columns. So not just the same length like vectors. They must be the same size. Again, this is for element by element operations. Again, we need a period used with multiplication, division, and exponentiation because the MATLAB defaults are matrix operations. And we'll actually talk about matrix multiplication in the next video. So we will start using some matrix math here, just simple matrix multiplication. So following are some examples of element by element operations using matrices. Scalar matrix multiplication. Here's a matrix called Fib. You'll notice it's full of Fibonacci numbers. And if we want to multiply each element in the matrix by 2, the command is simply 2 times fib. And we see the result is each element multiplied by 2. For addition and subtraction, again, we need to make sure we have equally sized matrices, and it works element by element. So here I've used the ones function to create a 3 by 3 matrix. So that looks like this. And that matrix is being subtracted from the fib matrix. So we're subtracting 1 from every element of the fib matrix. Here I've combined the two where I have a scalar times the matrix. So now this matrix here is all 3's. And then what's happening is we're adding 3 to every element of fib to get this result. For element by element multiplication, division, and exponentiation, the same as before, we need to have that period to do element by element. So here we have two matrices defined as A is equal to 1, 1, 2, 4, and B is equal to 5, 7, 3, 2. And we want to multiply each element of A by the corresponding element of B, and that will go in the corresponding space in the answer. So we have 1 times 5 goes there, and 1 times 7 goes there, etc. We can do the same thing with division and exponentiation. Again, we need that period. And here we have the same operation. So the first element in ADB2 is equal to 1 divided by 5 squared. And this element here would be equal to 1 divided by 7 squared. Again, working with the corresponding elements. It can be a little bit more challenging to visualize as we're working now with a matrix instead of a vector, but it's the same basic concept of element by element operations. Move on and talk about accessing matrix elements. Similar to vectors again, but now we're dealing with rows and columns in our indices. So for example, here's that matrix fib again, and if we want the middle element of fib, we'll take the element in, that would be the 5 here, that's in the second row and the second column, and so we assign that to what would be a scalar since it's a single element middle. Another example here using the colon operator and the end keyword. Let's say we want to take the lower 2 rows and write this in its most general form. We would say this, we could read this as the second to last through the last row, and that's this part, second to last through the last row, and then the comma indicates we're going to move on to the columns, and this, just having a colon there for the index for columns just means all columns. So we take the second to last rows and all columns and create this new matrix, lower 2 rows. We can combine that and do some math and logic with specific vector elements. Here we have a new matrix creation where we're taking the all rows, second through third columns of fib and dividing them element by element by the corresponding elements in all rows and first through second columns of fib. So you have to be paying special attention to your addressing here, which is a row, which is a column, and making sure to do this that the end results are the same size. we talked a little bit before with vectors about using logic or relational operators in element addressing, and we can do the same thing here. Here we say take all elements of the matrix GR that have a value greater than 1.65 and set them equal to 0. And so we see the result is this element and this element both have values greater than 1.65, so they're replaced by these two zeros. One thing that you do a lot when you're working with matrices is a concept called concatenation. Concatenation is the programming term for combining two matrices. One key here is that the result must be rectangular. So for example, if we want to combine those two matrices from the previous slide, fib and GR, we can combine them by taking GR and using this to add two columns to fib, and that's happening because these are separated by a comma, and the comma separates columns. So we can do that, and here's our result. But we can't use a semicolon because that separates rows. We can't add GR as additional rows to the matrix fib because GR only has two columns. So we get this error from MATLAB when we do that. So it's something to be careful with concatenation. Built-in functions, there's a few built-in functions that are useful for matrices. The vector functions we talked about when we were talking about vectors, such as sum, mean, and sort. These functions work column by column when the argument is a matrix and the result is a row vector. So for example, if you took the sum of a 3 by 3 matrix, the result would be a row vector that's 3 elements long, and each of those elements would be the sum of each column in the input. The find function, when used with matrices, you need to give that 2 output targets, one for the row and one for the column, as far as for the indices it returns. We talked about the find function with vectors, and in that case you only gave it one output variable because we only need one index to locate an element in a vector. Finally, the size function is a function that's useful for matrices. It's analogous. You'll use it the same way for matrices as you use the length function for vectors. And in this case, the size function returns a 2-element vector where the first is the number of rows and the second is the number of columns. So what you want to do, again, as we've been talking about all quarter, is use the help in MATLAB for the specific syntax and more details. So lastly, I just want to talk about expanding our main task when we're working with MATLAB is often to write functions, and expanding that to work with matrices. Very similar to vectors again, some guidelines. We want to make sure to use the period for element by element operations. We want to make sure to document any limitations on the matrix inputs, for example, limits on their size, in the help comments. We want to use the size function where needed to make sure our function works for any size matrix. And again, one of the points when we're writing functions is to write them as general as possible so that we can reuse them for multiple applications. So using that size function can help do that. In that same vein, using the end keyword when accessing elements near the end of the rows or columns of a matrix is also helpful. And that concludes this video on matrix operations.